Okay, let's dive right in. The paper we're looking at today is called Decoupled Q-Chunking, or DQC. It's by Kyung Lee, Sehong Park, and Sergey Levine. And it's making some serious waves in long horizon control.
It really is. I mean, if you've ever worked on complex robotics or any long horizon planning task, you have run straight into the brick wall of bootstrapping bias with traditional TD methods.
And DQC offers a really elegant way through that wall. So the camp insight here is getting that fast multi-step value learning you need for these long tasks.
Right.
Without crippling your policy's ability to react to what's happening. Because with TD methods, the value errors, they just compound backward. It's a huge problem over thousands of steps.
Exactly. And chunked critics, which, estimate the value of a sequence of actions, they sped up learning, but they introduced a whole new problem.
The policy constraint problem?
Yes. They forced the policy to spit out this long, open-loop sequence of actions, which is just terrible for reactivity and incredibly hard to train.
And DQC's solution is, well, it's to decouple things. You have a large critic chunk size, let's call it dollars, for fast value learning, but a much smaller policy chunk size, dollars.
So the policy only has to predict a short, manageable sequence. And it's trained against this special distilled critic that sort of summarizes the long-term value from the main big critic.
So you get the best of both worlds, the speed up from the big critic and a tractable reactive policy.
And empirically, it just works. DQC reliably outperforms the state-of-the-art on these really challenging OGBench tasks. It's a massive leap.
That sets the stage perfectly. So let's get into the technical details, starting with that classic problem that really forces this entire line of research, a bootstrapping bias.
Right. So TD methods are great. They let us estimate the value of an action without seeing the final reward. We just bootstrap from our estimate of the next state's value.
But the key word there is estimate, right? The value UQCSS is learned by regressing towards a target that itself contains another prediction.
Exactly. So if your prediction for Q ST plus 1 at T plus 1 is even slightly off.
That error gets baked right into your calculation for the current state, for 2S at dollar.
And in these long horizon tasks where your effective horizon dollars is just massive, these tiny errors snowball. They compound backward over hundreds, maybe thousands of steps.
Until the noise from the far future just completely overwhelms any real signal you have, learning becomes almost impossible.
It's a mess.
So I know one of the standard ways to fight this was using null-step returns, where you'd sum the actual rewards for, say, 9 steps before you bootstrap. That seems like it should help.
And it does, in theory. It definitely reduces the bias because you're pushing that noisy bootstrap target further into the future. You're relying more on real data. But in an offline setting, it introduces this other really nasty bias, off-policy bias.
Can you walk us through that?
So when you're calculating that null-step return, you're summing rewards along a trajectory from the data set. But the agent you're training now is different from the policy that collected that data.
Of course, that's the whole point of offline RL.
Right, so your null-step target is based on an off-policy trajectory. It doesn't actually reflect the value your current agent would get.
And I'm guessing the usual fix importance sampling doesn't work out so well here.
That's putting it mildly. Importance sampling is the technical equivalent of trying to weigh a whale with a bathroom scale. The variance just explodes.
So you end up with these unstable heuristics like truncating ratios, and you're just trading one kind of bias for another. It's just very hard to tune.
Which brings us to the next idea in this progression, the action chunking critic, or QC.
Right. Instead of estimating the value of a single action, you estimate the value of a whole sequence, Q, ST, ATT plus HI. How does that sidestep the off-policy problem?
Because it completely reframes the problem. It treats that entire chunk of actions, ATT plus H, as a single big, temporally extended action.
So if your chunk size dollars is, say, 10, you're now solving a problem where each time step is 10 times longer.
Exactly. And this lets you do an all-or-step backup, but without the off-policy bias, because you're only concerned with the transition from your start state TT to the end state CT plus HO. You've collapsed all those intermediate steps.
Okay, that's clever. You get the multi-step benefit without the importance sampling headache, but that leads directly to the policy constraint problem we mentioned earlier.
It does. If your critic is valuing a big chunk of size dollars, then your policy now has to produce that entire chunk all at once.
And that's where everything breaks down for the policy.
It's a huge conflict. We want a large dollar for good value propagation, but that makes the policy's job a nightmare. First, predicting the complex open-loop sequence of, say, 15 actions is just hard for a neural network.
And maybe more importantly, it just kills reactivity. The agent plans 15 steps ahead and then executes them blindly without checking the state if anything in the environment changes.
Your plan is obsolete after step 1, which is why you get such suboptimal behavior. And that's the exact dilemma DQC is built to solve.
So let's get into the DQC mechanism itself. The core idea is decoupling. We separate the critic's long value learning horizon, dollars, from the policy's short execution horizon, a dollar.
So the policy might only have to predict a single action, hot dollar 1, while the critic is still looking, say, 16 steps into the future.
The challenge then becomes, okay, how do you train that short-sighted policy to listen to the long-term wisdom of the critic?
The ideal objective would be to have the policy maximize the value of its short action chunk, ATT plus HA, assuming that this chunk is the best possible start to an optimal full chunk.
You're trying to maximize Kifi, STPT plus HA plus hot double.
Right, but look at that star term. Finding that optimal remainder sequence requires a whole internal optimization loop, which is just way too expensive to do at every training step.
And this is where the distillation comes in, with the specialized distilled critic, the QPT. So what's its job, conceptually?
I like to think of QPOs as the policy's specialized cheat sheet. The main critic, QPOs, is the authoritative source of truth. It holds the complex long-term value.
Okay.
QPO is a simpler network. It just takes the policy's short chunk and learns to approximate the best possible score that QPO would give that chunk if it were completed optimally.
So it's basically doing that expensive maximization search offline and then giving the policy a quick lookup value. How does it learn that approximation?
It's trained with an optimistic regression using expectile loss. This loss function implicitly performs that maximization by pushing the network to focus on the upper part, the upper quantiles of the full chunk Q values.
That sounds a lot like what implicit Q-learning, or IQL, does, using expectile regression to capture an optimistic upper bound.
It's the exact same tool, just used for a different purpose. IQL uses it to find the best actions in the dataset. DQC cleverly repurposes it to find the best continuation based on the full critic.
And once QP is trained, policy learning becomes simple. The policy just has to maximize the output of this distilled critic.
Exactly. You get a short horizon policy that's benefiting from long horizon planning without ever having to reason about that long horizon itself.
That distinction is so critical. Okay, let's shift to the theory, because the paper provides the first formal analysis of this whole action chunking idea.
Yes, and the analysis is centered on a condition they call open loop consistency, or OLC.
What is OLC actually measuring?
It's basically quantifying the gap between two things. The world you get if you just execute your planned actions open loop versus the world you actually see in your data set.
So if I plan a 10-step maneuver, OLC measures how much the real world is likely to deviate from my plan based on what I've seen before.
Precisely. In a perfectly predictable deterministic world, your OLC would be 0. In a chaotic one, it's large. And they distinguish between weak and strong OLC.
What's the difference?
Weak epsilon OLC is enough to guarantee that your critic's value estimate is stable and the bias is bounded, so your value function won't explode.
But, as Theorem 1 shows, a stable critic doesn't mean you get a good policy. You can have a critic that's learned perfectly stable values for terrible open-loop plans.
That's the failure mode of standard QC. That's why you need the stronger condition. Strong epsilon OLC.
And strong OLC guarantees.
What? It guarantees that your learned policy is actually near optimal. Theorem 3 shows that the suboptimality gap is bounded by this OLC bias. So if your open-loop plans are consistent with the data, your policy will be good.
This also lets them make a really strong theoretical comparison to standard n-step returns.
Yes. Proposition 2 is a key result. It says that action chunking Q-learning is provably better than n-step backup if your offline dataset is sufficiently suboptimal.
Why is that? Why does chunking handle bad data better?
Because the error for an n-step backup depends directly on how bad the actions in the dataset are. If you have terrible trajectories, your n-step targets are polluted.
Okay.
Chunking, because of its structure, bounds its error based on the OLC condition, how much the policy deviates for the data distribution, not on how suboptimal the data itself is.
So for anyone working with messy, mixed-quality offline datasets, chunking is just a more robust tool.
Absolutely. And this brings us back to DQC's closed-loop execution. Because the policy only outputs that short dollar to chunk, it gets to replan every few steps. It restores reactivity.
And the paper introduces another concept to formalize this benefit: bounded optimality variability, or BOV.
Right. BOV is basically the assumption that the best path forward doesn't change dramatically, even if you make a small, suboptimal move now.
That makes a lot of sense, especially in robotics. If I slightly misplace a block at the start of a long manipulation task, the overall goal is the same. I just have to adjust my immediate plan.
Exactly. And Theorem 5 proves that if your system has this property, DQC's closed-loop execution is near optimal. It formalizes why breaking that open-loop constraint is so powerful.
Okay, so that's the theory. How does this all look in practice? What does the DQC algorithm actually do?
It's a very practical algorithm, and it borrows a lot from IQL. First, they train a behavior cloning flow policy on the dataset. This just learns to mimic the data.
But that's not the final policy, right? It's more like a proposal generator.
Exactly. It's a way to stay close to the data distribution. The actual policy extraction happens at test time using best-of-dollar sampling.
Meaning they sample, say, 32 action chunks from that behavior policy.
And then they pick the one that gets the highest score from the distilled partial critic, QPBD. That's the action they execute.
Which is a really neat way to avoid explicitly training a policy network against a value function, which can be super unstable.
It is. And for updating the main critic, QPB, they use an implicit value backup. The target value for the next state, BT plus H, is also learned.
And here's the clever part, right? That value network, VD, is trained using quantile regression on the outputs of the distilled critic. Why that one?
Because it creates consistency. The policy is choosing an action based on the max of n samples from QPB. By training the value target using quantile regression on those same outputs, you're making the critic's update target align with what the policy is actually doing. It's very elegant.
And the empirical results are, frankly, pretty stunning. We're talking about OGBench, which has these incredibly hard tasks, like cube octuple, where you have to coordinate 8 objects, or humanoid maze giant with a 4,000-step horizon.
The performance jump is just undeniable. Across the hardest environments, DQC scores an 82. The previous state-of-the-art, Sharsa, was at 68, and standard action chunking QC was way down to 25.
That is a massive improvement.
It's a huge leap in policy reliability on problems that were, until recently, almost unsolvable.
And the ablations seem to really back up the design choices. What did they find about the distilled critic? Is it really necessary?
Oh, it's absolutely essential.
Yeah.
They tested against a version without the specific expectile distillation, and DQC was consistently better. That explicit training of QPC to capture the optimistic extension is what makes the whole thing work.
And what about hyperparameters? What do people need to know if they want to implement this?
2 big things. First, you need sufficient optimism. The parameters kappa-pod and kappa-pod for the regression losses have to be set to push towards the upper quantiles. If you set them to 0.5, which is neutral, performance just collapses.
You have to be optimistic. And the second thing,
The compute. DQC relies on sampling, so it needs a large batch size. They used 49.6 and a decent number of samples for the best of n part, so dollars of $32 or more. This is not a method that's going to work well on a small budget.
so at the end of the day, this framework seems like a really powerful blueprint. We've combined the fast value propagation from chunked critics with the high reactivity of short policies.
It's a huge step forward for long horizon control. But, and the authors point this out themselves, DQC still uses fixed chunk sizes at $1 for all states.
And that's probably not optimal, right? The ideal planning horizon must change depending on what's happening.
Of course, if you're navigating an open hallway, a long open loop plan is fine. If you're trying to thread a needle, you need single-step reactivity.
So I guess the final provocative thought here is that the next frontier has to be dynamic, state-dependent chunking.
Exactly. Imagine an agent that can decide for itself how far to look ahead based on the complexity of its current situation, developing methods that can support flexible chunk sizes.
That would be the ultimate combination of planning efficiency and reactive control.
It would be. And it's a monumental but very exciting challenge for future research.